Hey, happy Equinox Ignite students. It's going to be a good day. We've got a lot to learn. We're going to start with some history. We're going to learn about ancient astronomy, how things move, Newton, Kepler, and, the day the Earth moved from the center of everything. So we're not important anymore. All right, here we go. The ancients, and when we say ancients, I mean like every ancient culture, whether it's Chinese astronomy, Islamic astronomy, European astronomy, Mayan, every ancient culture looked to the sky to navigate, to plant crops, to have a calendar. This is not a new thing. It didn't take the invention of a telescope to come up with looking up at night. What else are you going to do? You're bored. Okay, you don't have this. There's no charging the cell phone that doesn't have, right? There's nothing. So you look up at night and you see the moon, and then you see these 5 other crazy lights that move around the sky that are different than the stars, because the stars they understood, and the stars change with the seasons. But then there's these 5 other things: Mercury, Venus, Earth, we're going to skip Earth, Mars, Jupiter, and Saturn. So that's 6 if we count Earth, but it's 5 other things. This is the 5 closest planets. Every ancient culture knew those 5 things and knew those 5 dots were different than stars because they have these weird motions. So if Earth is making a circle around the sun and Mars is making a circle around the sun, Earth is going to go around faster than Mars. And so when Earth is catching up, passing, and then going past Mars, Mars starts to do this weird loop in the sky. It's called retrograde motion. Let's take a look real fast here. This is astronomy picture of the day. It's a NASA thing. This is a time lapse, and I'll hold still, and the other stuff. Yep, there we go. This line, so there's January 31st, February 8th, 14th. So these are, a week apart running. This is the motion of Mars, and then it all of a sudden goes backwards, and then it goes forward again compared to the stars. Now, sun rises in the east, sets in the west. The moon rises in the east, sets in the west. The stars every night come up in the east and set in the west, and you can track that over 12 hours of darkness or 12 hours of daylight for the sun or the moon. That's fine. But slowly over seasons, the stars, the constellations, shift. And what's visible in the winter may not be visible all summer, or they change positions. That happens over a year. But all this Mars is going forward. It's moving against the constellations. So these 5 bright lights move separate from all the constellations which have the normal motion. So here you look up in, January, February, and Mars is way over here in the middle of Libra. And then a month later, you look up and it's changed constellations. And then you look up and all of a sudden it's moving the opposite direction. And then it hooks around and comes back. This took 9 months, 8 months to get from this first picture to here. And so Mars, the motion of Mars, this is prograde, this is normal, retrograde motion, and back to prograde motion. Saturn did the same thing during 2016. It's less obvious when Saturn has prograde or retrograde motion, other than it just kind of eases back and forth, has a little weave in its step. All right, here you go. Try this one. One more time. There we go. Every 2.5 days in here, red dot's Mars. You can see the moon goes across because that's 1 month. The moon flies across, that's month 2. Moon, that's 3. Here we go. And Mars now, this is retrograde motion. You can see the dots get closer together as it spins around. So this is Earth and Mars are doing a circle. And as we pass it, it keeps going. And then it keeps going again. If you're driving down the highway and you're going to pass a truck, it could look like the truck is suddenly going backwards relative to you. That's all that was. That's what retrograde motion is. Then we got to put it in a circle. So the circle thing's a little different. Okay. Planet comes from the Greek word planetes. It means wanderer. So they knew those 5 things were planets, or named them planets, separate from the stars. They get their own set of names. And so that goes back to the ancient Greeks, where the modern English word comes from. Every ancient culture knew that those 5 things were different than the rest. Venus is the 3rd brightest thing in the sky. The sun, the moon, Venus. It beats any star. It beats any other planet. Venus is sun, the moon that we always kind of skip over when we talk about the brightest thing in the night sky. No, sun, moon, Venus is next. By far, the next brightest thing entirely in the sky. Venus goes around the sun inside of Earth. So in the middle of the night, you're never going to look straight up and see Venus, because Venus is by the sun and the sun's on the other side of Earth. So Venus, you're either going to see right before and after sunset, or right before and after dawn. Same thing with Mercury, but even shorter time frame because it's closer to the sun. So Mercury and Venus are close. Mars, Jupiter, Saturn are further out. So you've got 3 nighttime planets, and you got 2 daytime planets that let's call them twilight planets. All right. These things move different. And so that's one of the basics where all this comes from. Let's go. I've got something new for you. We're going to try this. I'm going to get you a link to this. I have no idea what Histropedia was before this morning. Seemed pretty cool. We've got a timeline. Here we go. Zoom out. You can see the year 2000. Here's 400 BC. All of this is going on. When we say ancient astronomy, this is what we mean. Let's shrink that down. And let's see if we can do that. Get rid of some. There we go. First of all, we're going back. S-P-A, Socrates, Plato, and Aristotle. I have no idea. This was one of the craziest things, and I didn't learn it till I was significantly older. Socrates, Plato, and Aristotle, the 3 ancient Greek philosophers, were not just 3 random guys in 3 random times. They literally walked and talked with each other. If you look here, Socrates was alive and taught Plato. Plato was alive and taught Aristotle. They were students of each other. 3 of the greatest names in all of philosophy and ancient history were on the same city at the same time, within 100 years of each other. It's absolutely wild that they learned from each other, and the amount of knowledge that was built back then. But the end of this, most of this is credited to Aristotle. Circles. The idea that circles are perfect, they're natural, they're beautiful, they're seen. Circles. So the Earth's in the middle and the sun goes around us in a circle. And the other stars go around us in these circles, and the planets go around us in these circles, but they're not quite right. All right, there's this other guy right here, Aristarchus. Okay, he actually said the other way. He said, no, the sun's in the middle and Earth goes around the sun. But Aristotle was too big, too famous. No one paid attention to this guy at all. And we're going to zoom out here. 50 years, 50 years, 50 years, 50 years, 50 years. Here we go. 400 BC to 100 AD. Ptolemy, silent P. Ptolemy is the first guy who comes around and says, I can do it. I can make a map. We're going to put the Earth in the middle, and we're going to put the sun on a circle. And then he made circles of circles, like a spirograph. So he put a little circle somewhere about the middle of Mars, and then he put a smaller circle on it, and he used it like a spirograph, and it did this kind of thing, or maybe I could do it. So it would do this as it goes around Earth, and that's how he was able to get that forward and backwards motion through the night sky. And he changed the size of the big circle, little circle relative to each one. And Ptolemy actually came up with a fairly predictive, meaning he drew a map and then he put dates on it and he says, hey, in 3 months, Mars is going to start doing that backwards thing again. And it was fairly right. It was pretty accurate. That was awesome. So it was flat wrong, but it was predictive. So you're turning this from ideas into science because it was one of the first ones that was testable. He's like, look, I think this is when this is going to happen in the future. Here's when it happened in the past. Let's test it. Let's see how accurate this is. And the geocentric, geo-Earth, Earth-centered model of the universe begins to come into play. All right, let's zoom back out here. So we've got 50 years, 50 years, 50 years. Hey, 100 AD, nothing, 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 nothing. Nobody challenges this until Copernicus comes along. It's called the Copernican Revolution because Nicholas Copernicus was the guy who kicked all of this off and says heliocentric. Helio, the sun, is in the middle. So let's zoom out real quick. I mean, I'm trying to be... Here's the year 2000. So all of this happens in a little bitty thing right here. So from here at 300 BC, all the way till 1400 with Nicholas Copernicus, everybody just assumed the Earth is in the middle. Everybody except for these couple guys, Aristarchus of Samoa. All right, Copernicus comes along. Copernicus comes along in 1400. Everything's good. Born in 1473. Right here. This is Copernicus writing out the heliocentric model, and everything's good, except we notice the end of his timeline. And there's a gap. Nobody picks this up. Nobody knows about it. Nobody's really reading it. Aristotle still has sway over all of this stuff. Then Tycho Brahi comes along. Okay? Now, Brahi is a rich nobleman. For good, bad, or worse, lots of the old scientists were rich noblemen because no one else could afford to just sit around and do these experiments all day. And no one else could afford assistance or the lab equipment or any of the other stuff. But does that make them good or bad people? That's another class. We're going to focus on this. All right. Tycho Brahe, we can open this up. And here you go. Let's get a little bit. There we go. So he is Danish, nobleman, astronomer. He is a very, very accurate astronomer. His observations are some of the best data recorded. Remember, there's no telescope at this point. There's nothing. You look at this, you go out at night and you measure up and you measure over and you write down where you saw the thing and what time it was. That's it. How did he do this? Well, Johannes Kepler comes along, and Kepler is Brahe's assistant. Kepler's a great astronomer, but Kepler is also more of a mathematician. So after Brahe dies, Kepler goes back inside and does his day job and does the math and comes up with Kepler's laws. We're going to talk about Kepler's laws in a little bit. Now, in between all this, Galileo. So we can look at our timeline here. We can look at the lines. Galileo lived significantly longer than the other two, right? Brahe dies. Brahe was a great observationalist. He observed and wrote down all this stuff. Kepler, red line, comes along and does the math with it. But Galileo, much bigger impact across more disciplines, right? And a much longer life. So used the data from these other two. We can even zoom in a little bit here. We're getting into some interesting stuff. Kepler publishes right here 1609 to 1619. It took him 10 years to publish like 3 volumes of his data. He and Tycho Brahe's data. He used the data where he was working with Tycho to publish this, the laws of planetary motion. Laws of Tycho. You know what? Here you go. Kepler's laws. Okay. First law. The orbit of a planet is an ellipse with the sun at the center. Okay, I know that says foci. We're going to pause and we're going to ignore that. Kepler wrote at the center. So what? So it's an oval. Who cares? Because for over 1,000 years, in fact, 300 plus 1,400, see, we're at 1,700 years, the circle has been perfect. The circle is ideal. It is perfect. Why are we going to smush this and say, no, the planets really go around in ovals? Ovals? Why? There's no need for that. That seems really subtle and really minor, but it was a huge overthrow to 1,700 years worth of tradition where everyone just knew that these were perfect circles. And they're really, really, really close to perfect circles, but they're not. All right. Kepler's law number 2, equal area in equal time. Here's what we're going to do. We're going to look at just this purple image right here. And if we drew this triangle, we looked at here, straight line from the sun, and then we did it again over here. And the planet's going to go around this purple circle. You can make a triangle. I know that's curved outside, but we can approximate. And you can make another triangle over here. So you've got a short, fat one and a tall, skinny one. If the area of triangle 1 and the area of triangle 2, like half base times height, the amount of shaded stuff, if those areas are equal, then it takes the planet the same amount of time to go across the outside. So to get from here to here would take 1 month, and to get from here to here would take 1 month. You're like, wait a minute. That means the planet's slow out here in these tall, skinny triangles, and it's fast over here in these short, fat triangles. Yep. I'm going to give you a link to some visualizations of this, okay? But the planets, as they go around the sun, they slow down, turn around. The sun's pulling them with gravity. They speed up, and do a quick 180 drift around here. And then they slow down as they move away. Slow. And then they decide to make the turn and ease back. And then they hit the gas, and then they come around, drift around the corner, and go and do it again. Second law. Equal areas, equal shaded areas, mean equal time. Third law, p squared proportional to a cubed. The square of a planet's period, the time it takes it to go around, is proportional to the cube of the length of the semi-major axis. Okay, semi-major axis, think radius. Radius. I know these are ovals, but they're really close to circles because they're not squished that much. So think radius. So radius squared is proportional to period cubed. Kepler did not know how far it was to any single planet or the sun or anything else. He knew all of the times. If we know how long it takes Earth to go around the sun, we can track, and it takes Mars 1.5 times that. He just put a ratio and said the time to go around for Earth and Mars to go around, we're going to square that, and p squared, is proportional to the radius of Earth to Mars cubed. So if it takes 1.5 times to go, if Mars is 1.5 years, you put that over here and you square those, you could come up with the distance to Mars. Not the distance in miles or meters or anything, but you would know that it's twice as far as Earth is from the sun. So twice as far comes up to 1.5 years. He knew all the ratios, but none of the exact values. Really impressive, really think. So I hid something earlier. In fact, I'm going to keep it hidden. This is another pamphlet published. Here we go. Starry Messenger, Starry Night. This is published by Galileo in 1610, so a year after Kepler's first book, but before Kepler published the last book. This is the first work with the telescope. Galileo did not invent the telescope. He heard about this discovery for like a spyglass. Think pirates in a long scope in Holland. I'm pretty sure Holland, in Dutch, right? The Amsterdam. And without ever seeing one, he made one. Galileo was the first guy to take it. Instead of looking at distant land, he was the first guy to look up with it, and absolutely the first guy to publish data about it here in 1610. Galileo found that Jupiter had 4 moons: Io, Europa, Ganymede, and Callisto. They are the 4 Galilean moons. They're really important because he's like, oh my gosh, if even Jupiter has moons, why would the Earth be in center? Why is Earth important? If this other planet out there has moons, why isn't it in the center? Why isn't the sun in the center? Let's put the sun in the center. He looked at the moon and found that it had craters and valleys and all these other things, and it just started to come together. He did the first observations with that. Look, there's even a little gap here, and then we get to Newton. All right? We get to Newton, and then big stuff happens. Now, remember, just because Newton's alive here, you got to give him a few years until he starts doing his math. In fact, right here, this 1687 is when Newton publishes Newton's laws. This is Principia, all right, the natural principle mathematician. So this is it, and then this is Newton's laws, published in a couple volumes. If you want to learn about history, Catherine Barton is Newton's niece / lab assistant. And then she goes on to marry a famous politician, and there's all sorts of stuff. If you want to get a detail into history, read up on Catherine Barton there. But Newton's laws of motion, 1687, Newton's laws of motion, he corrects one of Kepler's laws. So the thing I hid earlier, it said, Kepler originally said, planets orbit the sun in an ellipse with the sun at the center. Or the sun at a focus, the sun at the focus, because an ellipse has 2 foci. And Newton says, no, they don't. Newton says, no, they don't. Newton says that the sun isn't in the center, but the center of mass is in the center. What in the world? Hold on, let me back up just a step here. All right, learn about mirror images. Here we go. Sun, planet. All right, not to scale, but if we balance this, that's the center of mass. This is mass. This is heavier, but we got a longer thing out there to the sun. Kepler said, look, we're going to put the sun right here at the focus of our ellipse, and then this is going to go around and make an oval. Okay? I know this red bar would make a circle, but the planet would go further than less, and it would make an oval around the sun. Newton comes along, 1687, and says, no, the sun isn't at the focus. The center of mass, this part right here, is at the focus. So really, this happens. The sun also revolves around this imaginary spot in space that mathematically is calculated. The sun moves. It revolves around this thing too. You're like, the sun does not move. The sun goes up in the sky and comes down in the sky. No. This is entirely different. Here's the thing. This was really astounding, and no one predicted this because the sun is so massive. The center of mass isn't out here. This is a demonstration. The center of mass is like right here. So really the sun doesn't go in a big circle. The sun just kind of wobbles, right? That's all the sun does. The sun does a nice little wobble around the center of mass in the system. So that was Newton's correction to Kepler's law. So even Kepler's law got adjusted there. We have gone through a boatload of history, and there's a whole lot more. But this, let's zoom back out here, is the Copernican Revolution. This is the idea that all this stuff happened from the late 1400s through 1687 when Newton published, right? All of that stuff happened to overturn what the ancient philosophers had said in 300 BC. All right, there is the history of modern astronomy, and we go through to Galileo, and once we get to telescope, observations take off, and then things go fast from there. All right, Have a good day, guys.